Hello and welcome to today's physics lecture wherein we shall be dealing with the B or the magnetic field, how the magnetic field is for a toroidal solenoid. As in the case of toroidal solenoid, we have to understand that over there the magnetic induction occurs under how the things actually take place. First of all, about the toroidal solenoid, what is this toroidal all about? We have seen the solenoid. But what is about the toroidal solenoid? Why is it called toroidal solenoid? To take the example, if we take any, say for example, line of finite length, obviously if we do not say the starting and the ending point, obviously there would be a finite distance between any starting point and any ending point if a line is being taken. But if instead we take three or more lines, as such they form a loop. Obviously if we take, say for example, a triangle or a circle, it has got its perimeter, which means that obviously it has got a definite length. But if the starting point and the ending point is not defined over there, a person who will be roaming in that path will be infinite. The roaming will be infinite, but the perimeter is finite. So, likewise is a case for solenoid, that if we are able to devise the solenoid as such that it forms a likely loop, which means that this has taken in the case of an endless solenoid. So the toroidal solenoid is one such, which is also known as endless solenoid. So let us see that how it actually looks like. Say for example over here, the best way to draw the diagram of a toroidal solenoid is just form two concentric circles, and over there, say for example, a line is being made, and then likewise these are the solenoids. So this solenoid is forming, and as we know that in the solenoid that there is a definite B associated at each and every point, and we shall be understanding those B's now at various locations. So this is the case of a toroidal solenoid. If over here the current enters, likewise it will go round and round and round and round via this solenoid until it comes at this point, and this I will actually go like this. So this solenoid has got several points. The first point will be, say for example, anywhere which is inside. Say for example we take an inside circle and mark a point, say for example a point of A. We wish to find out that due to the magnetic induction which is happening due to the flowing of current, that what will be the B or the magnetic field at point A. The second case, it could be that what would be the, say like the magnetic field on the interior region of this solenoid, marked by these black dotted lines. So say for example we take any point on it and say it as, say, point P. And obviously there would be another concentric circle, but this one shall lie outside this one, and we also wish to find out the value of B at this point. Say for example we do take a point over here marked as Q. So we wish to find out that what would be the value of the magnetic field at point A, at point P and at point Q due to the flow of current in this case of a toroidal solenoid. It is very easy for us to find out if we do consider as per the equation we got that the line integral of the magnetic field at any over closed region is simply equals to the permeability times the current is flowing through it, right? So we can say that by Ampere's circuital law, integration of B dl will be equals to mu naught times the current that is flowing through it. It is mu naught I. Now say for example, I have written over here I dash and not as I. It is because of the very reason that first of all we have to mark out this dl for the small region at which we are concentrated in. So let us check this small region as like this, right? So this one over here would be dl, and if it is said that per unit length, if it is said that n is equals to number of turns, because these are turns, the number of turns per unit length. And if this happens out, then obviously how many number of turns are there in this? Say for example, this is capital N multiplied by dl, right? So we can find out, and if we take that n, the small n is equals to number of turns in entire toroidal solenoid. So if we are now integrating this entire dl, we need to add up all the dl's now, and adding up all the dl's we did find out that the actual value or the number of turns for this solenoid will be equals to small n, right? So the amount of current that will be passing this I dash will simply be equals to, as it was said, that whatever you find out the B for one loop, if it is for n number of loops, simply multiplied by n. Why? Because right over here we can see that I dash now will be equals to the I, this what is flowing, multiplied by the number of loops in the entire toroidal solenoid. That will be equals to I multiplied by n. So over here we could do is that integration of B dl over this closed surface. Now whatever the closed surface we are taking the closed surface of this dotted line right now. Okay, we are not taking the closed surface of this, or we are not taking the closed surface of this, because we intend to find out the B at point P. Say for B at point P we intend to find out, right? So this will be equals to mu naught times the total current, that is equals to I multiplied by n. Now for this, what will be the perimeter? If say for example from the center, if the radius of this point, say this is the center, if the radius is say for example small r, So the entire this closed interval, the perimeter will be simply equals to 2 pi r. So integration of the dl, we can write it as b at point P multiplied by 2 pi r will be equals to mu naught n I. Right? Or we can write it as that b at point P now will be equals to mu naught n I divided by 2 pi r. So this is the expression for the B or the magnetic field at any point P over this closed surface, right? Not on this A or not on this Q. Closely observe that for the case of solenoid, we did found out if it was like infinitely long solenoid, at that time any point which is at the center was found out to be mu naught Ni, where N is the number of the lobe. Okay. Over here we did found out that Bp is equal to mu naught Ni divided by 2 pi r, which means that if we are going to make this endless solenoid or the toroidal solenoid much bigger, then it will be a circle like this. There will be a center over here and the radius will be much more, right? So for the toroidal solenoid, if it is small, the B expression for the magnetic field will be greater, as we could see that the B is inversely proportional to the R. So for a small toroidal solenoid, the B will be larger, but for a bigger toroidal solenoid, obviously the B at the center of the toroidal solenoid will be actually lesser. So we can conclude that length of solenoid is actually inversely proportional to induced magnetic field intensity. Or we may write it as B, right? Now this is actually for the case of this point P. Now if we do wish to find out that what will be the B for A, we could find it out. So integration of B at A dl will be equals to mu naught I dash. Now what will be the I dash for this region? Is any current flowing in this region, over this region? Is any current flowing through over here? No. So the value of I dash will simply be equals to 0. So this entire expression will come out to be 0, which means that BA will be equal to 0, which implies that BA will be equals to 0. Now let us find out that what is the value of BQ at this point Q. What is the value of the magnetic field intensity of B, right? Now if we do wish to find out, obviously we could find out as the integration of BQ dl, it will be equals to mu naught multiplied by I dash. Now closely observe that in this entire region, the entire solenoid is over there, right? Which means if you do take a very small region, let us take this very small region. At this very small region, if we observe closely, we will find that this I is on this direction, again this I on this direction, again this I on this direction. But while this I was going from over here to over here, the direction just changed. So this I was cancelling out this I. Because if you want to observe it, see, what is happening is that over here, say the I is coming like this, and the same value of I is going up. Because the value of I won't change anywhere, right? Because these are in series. So this I will cancel out this I. Now again it will go over here, and again it will come back in the opposite direction. It will cancel out. Likewise the scenario for each and every loop. So the value of I dash at this point Q will simply be equals to 0 because they are cancelling out, right? Which implies that this expression will be equals to 0 because this is I dash, or we can write that V at point Q is simply equals to 0. Now from this we got to know that if ever we find out anything such as that the line integral of BDL is equals to 0, it does not always mean that it does not have current flowing through it. Because obviously here we did find out that there was current. That is the reason why it was 0. But at this particular point, we did observe that there were currents, but they were cancelling out. First thing. Second thing, if ever we find out that the integration of the line integration of B over very closed loop is equals to 0, never conclude with the confirmation that over there B is equals to 0. It is that the area where you are taking the line integral of all the B taken is equals to 0, but that does not mean that the B is 0 at all the point. It may be possible, say for example, you are taking this smaller region over here. The red dots indicate, like say for example there are 6 red dots which indicate that magnetic fields are coming out like this, right? But if you are going to take, say for example, the line integral over this, and you found out that this is the scenario that 6B are also going inside. So it means that the line integral of B over this region is equals to 0, but that does not really mean that at every point the B is 0. So from the case of the toroidal solenoid, we are also able to understand that if the line integral of B is equals to 0, it means that over here it could be possible that there is no current at all, or it might be possible that one current, that the loop currents are actually cancelling each other, or it might be possible that over there was no B, or there is B, but in the line integral over that closed region, the integration of the B's, of all the B's, is simply equals to 0. Right? Thank you.